Hey guys, today you will continue in our series where we go through the courses in FPGA Academy, and today you will learn about 8-bit accumulator circuit, and then we will try to implement it in VHDL. You might be asking, why would I want to learn about this type of circuit? For example, in convolutional neural networks, which is type of network used for object detection and classification, you need to perform convolution operation, and if you would try to implement this operation in FPGA, it could look something like this. You will perform the operation on a matrix. The matrix can be, for example, your image, and you will have kernel of some size. So for example, in this case, it's size 9 or 3 times 3, and each of the cells in the kernel gets multiplied by the kernel value, by the corresponding kernel value. So each of the cell has their own multiplier here. So you multiply each of the cells by some value, and then you need to sum all of the results. So each of the multiplication results you need to sum, and for that you would use the accumulator here. So that's an example of accumulator used in CNN. Another use case of accumulator could be in digital to analog converter. If you want to generate a wave as an analog signal, for example, a sine wave, you would have first a phase accumulator that will get some value from a register that controls the frequency. And this accumulator gives you the phase. So for example, here we have some phase. For sine, this would be 2 pi, and it would repeat. So you would have some phase here, and this phase would get translated in the phase to amplitude converter to amplitude value. So first you would have your phase here. For that, you would use the accumulator circuit. Then you would convert the phase to amplitude, and this amplitude would get converted to analog signals, so to actual voltage value. And so you could use the accumulator for the generating of sine or other waves. And now let's look at the actual accumulator circuit. The main part is the adder here that adds two numbers, two inputs, and gives you output that is saved to this register. And the output of this register is inputted back as a first or as one of the inputs, and the second input is some value a. So for example, let's say we start here with 0 and this will be 2. That means that we add 2 to 0 and we change the value in register to 2, and then 2 gets inputted back, and 2 plus 2 is 4, then 6, 7, 8, and so on. So you just increase the value in this register by 2. You can then change this value, so you will have 8 here. You can change it to 3, and then it will increase by 3, and so on. So that's how you can increment the value here, and it's called accumulator because you accumulate the value. Then we have some clock here that will drive the whole design, and we will also output overflow and carry. In our design, the value A will be set by switches, the clock will be driven by key, and we will show the output on the 7-segment displays. We will also show the value of the register A on the 7-segment displays, and then we will display on the LEDs overflow and carry from the adder. So let's look at how we can implement this in VHDL. The accumulator is part of Lab 6 adders, subtractors, and multipliers. And if you haven't seen the previous labs, you can find them on my YouTube channel. Last time we learned about timing analysis in quarters, and you can find the other labs in my previous videos. So let's begin with quarters. Here I have already set up a project with part 1. So that will be for part 1 in the lab 6, where we will try to implement accumulator, and then we will try to implement also part 2, where we will introduce subtraction. So here you have a value, and if this value is 0, we will add these two numbers. If it's 1, then we will subtract the A value from the value in the register. So if in the register you have 10, here you have 2, the next value will be 8. If it's 1, if it's 0, the next value will be 12. So let's look at how we can implement it. I will start with creating a new VHDL file, and this file will be called accumulator 8-bit. 8-bit. And let's look at the inputs. So our accumulator will include this whole circuit. So as input, in the first part, we will have some number A, then clock. A will be 8-bit, clock will be 1-bit, and then as output we will have overflow and carry, that's just 1 bit, and then some number that will be also 8 bits. And in the second part, we will introduce this switcher that will switch between addition and subtraction. So I will change these. So we will have some input. I will call it data in, and it will be 7 down to 0. Then we will have one more input, that will be clock, and also we need reset, and we will reset when the reset is 0, so I will call it reset n, and this will be just std logic. And then we have outputs, and output will be another data out, another number, and it will be also 7 down to 0. We can also do generic, so we don't have to specify the number here. We can just write n, it will be natural, and the value will be 8. So here I will write n minus 1, n minus 1. So this will specify the length of the input and output. And then we also need the overflow and carry outputs, and this will be std logic. So these are our inputs and outputs. And now let's we don't need this. First I will create the registers for each of the values. As you can see here, I have 1, 2, 3, and 4 registers, each of them holding some value. So I will have signal called data at, that will be this register here, and this register will be this value. Then I need one more that will be called data register, and then I need 2 more std logic. I'll create it like this, and this will be our overflow rack, and our carry register. So we have 4 registers here, and we will, by default, we will give them 0 value, others 0. Can do this same here, and this will be also by default 0. Now I will save it, and I will save it as accumulator 8-bit, or we can just call it accumulator, and we can change this to, because since we have the generic value here, we don't have to specify the size. So let's call it accumulator, and then we will create here a process. Process that will change on the clock and also on reset n. If reset n is equal to, and we will reset it if it's equal to 0, else if rising edge of clock, then we do something, and if. So if the reset is equal to n, we will reset all the registers. So data will be set to 0, and let's do it for all of the 4 values, or all of the 4 registers. So data rack of rack will be 0, and C rack will be also 0, and on the rising edge, we will increment the accumulator. I will create a new signal here called sum. That will be this this signal here. This will be sum, and the sum will be, it will not actually be n-1, it will be 1 bigger, and the last or the most significant bit in this case will be the carry. So we need one more for the carry, and I will use this outside of the clock, because if you look at the circuit here, you can see there is no clock as input to the adder, so we don't need it inside of the clock. And this will add data add plus data rec. But this will actually be signed number, and the signed number can start, if you look at here, this is the representation of signed numbers. It's the 2's complement binary. So if you look at the first most significant bit here, if it's 0, it means it's positive, and if it starts with 1, it means it's negative. And the sum here is 1 bigger than the data add and data register, so we can't add it because it would be, the size would be one smaller. This is n-1 and this is n. So we need to create an extended version, but we can't just extend it like here by 0, because we don't know if it's negative or positive. And if you extend it by 0, you would change the sign. If it would be negative, it would start with 1, so you need to add 1 as most significant bit so you don't change the sign. So I need to use or I need to create some values that will hold the bigger ones. So I will create here, and I will call it extend or x this. So this is extended version, and here I will assign them. You can use resize for this, and this function takes the original one, so data add, and here some size, so that will be the length of the sum. And I will do the same for the other one. And then I will add these two here. And the sum will be actually signed as well. So we have our sum here that gets you from these values, and our carry, or yeah, let's assign here carry will be the output from the carry register, and overflow will be the output, or will be driven by overflow register, like this. And let's assign these two now. And yeah, so on the rising edge of the clock, we need to change the values of all the registers. So let's begin with this register here. This register on the rising edge gets the value from the adder. So data rec, that's the name of the register, will get the value of the sum, but the sum is too big in this case, so we can say 7 down to 0 or n-1. Then data add will get a new value, and this value will be the data in, and we will change it to signed. And then we need to assign carry and overflow. Carry will be the value of sum n, so the most significant bit, and overflow will be, so overflow happens in signed numbers when you add two positive numbers that start with 0 and you get negative number which starts with 1. Or if you add two negative numbers, so for example you add -7 and -3, you would expect to get -10. So you need to get negative number, but you would get positive number. That means overflow happened. So we will implement it using logic. So if not data add, so if the most significant bit of the data add is 0 and not data register and -1. So if the most significant bits of the two numbers are 0 and the sum n-1 is positive, then we get overflow. Or we can copy this and just change. Or if this is 1 and this is also 1 and we get not sum, so if the most significant bits of these two are 1 and this is 0, then we also get overflow. So our overflow carry data add, data register, and we also need to drive the data out here, and that will be std logic vector. We need to convert the signed to std logic vector, and this will be data rec. So I think this is all. We add the two numbers, and on the rising edge we change the register, we change the new value, the new, this register represent this register here, so we get the value from the switches, and carry and overflow. I think this is all for the accumulator. I will copy this as an entity into our design here, or as a component and component. And let's design this part. So I will create accumulator instance 0. It will be of type accumulator, port map, and we don't need to map the generic because we are satisfied with 8. So we will port map the other inputs and outputs. Data in will be switches 7 down to 0. Then we have clock. Clock will be key 1, key 1, 1. Then we have reset. Reset will be key 0. And we have outputs. So I will create or overflow and carry. So overflow, let's look at the assignment here. And overflow signal should be displayed on LEDR9. So overflow LEDR9. Then carry will be LEDR8. And data out, let's save it to a signal called A. And this will be std logic vector. And we need, so A, no, this is S actually, S here. And let's display S on 7-segment displays. So I will create segment 0. It will be 7, how it's called here, port map. This takes as input some number, so that will be S. 7 down to 4. And then hex. So this will be hex 1. And call it also 1 here. This will be segment 0. And this will be 3 down to 0. And hex 0. We also need to display the value of the we need to also display the value of the input. So in the assignment, they want us to output this value, but since this is inside of the accumulator, I can't display this, so I will just display this value, so immediate value of the switches. So let's display the value of the switches on the 7 segment displays, or yeah, let's display it on the 7 segment displays. So this will be 3 and 2, 3 and 2, and this will be switches 7 down to 0 and switches 3 down to 0. Yes. I think so. So this is our sum, yes, and then switches, and we also display them on LDR. LDR 7 down to 0 will be switches 7 down to 0. Or do we want to display the output? Yeah, let's display the output here. So the output will be displayed on the LEDRs, the input on these two 7 segment displays, and then the output on also on these two 7 segment displays. I think this is all, and we can try to compile. And we have a typo. I need to add semicolon here. I'll add it here and also in the accumulator for the generic value. And one more typo here. This is not then but begin. So like this. The compilation is done. So if you look at the steps, we have finished 1, 2, and 3 in the first part. And in the fourth one, we are supposed to use timing simulation to verify the correct operation of the circuit. So let's do it now. If you look at the timing analyzer here, we can see that we haven't passed the simulation. The maximum frequency for our clock is 428 megahertz. And that's because, and we haven't passed, and that's because the period by default is set to 1, which means 1000 megahertz clock. So the maximum is around 400, and we set the timing simulation to 1000 megahertz. So we haven't passed. So we can change this. If you don't know what I'm talking about now, you can look at the previous video where I go through the timing analysis in quarters. And let's look at how we can change this so we can pass. So I will open the timing analyzer, and here the period is set to 1 nanosecond, so I will change it to 20, which will change it to 50 megahertz. And if you look at the clock, you can see it's kind of weird. We have this one spike to 1, and then it's 0 for a long time, and that's because here we have set the time for the edges. So if I delete this, it will be 50% in 1 and 50% in 0. So we can keep it like this, and I will press run. And now I have to press here update timing netlist, then report setup summary. We can look at the slack and we can see it's positive, which means we have passed the simulation. And I will write it to SDC file like this. Okay. And I will close this. No. Then I will open settings here under assignment. Go to timing analyzer, and here I will add the value that we have just made, the file. Apply, okay. And what this will do is when I run the compilation again, it will automatically check using this settings for the timing simulation, so it will perform the timing simulation automatically. And this can increase the speed of your compilation, because once it finds solution that satisfies the clock, it will stop. But if you have really strict constraint, it will try to look for a really good solution that will satisfy it, and it will take longer. So let's do it now, and let's run the compilation again. Compilation is done. I will program the board. And let's look at it together. So here you can see the board, and you can see there are just zeros on the display. I hope you can see it. You can see there are 4 zeros. So that's our input and our output. So using the switches, I will set them to 3. So you can see the value there change to 3. And when I press the clock, we will add the 3 to our accumulator. So you can see 3 and 6, 9, and you can see it's counting. And you can see that now the value doesn't show the next value, because it only shows numbers from 0 to 9. So we need to implement that for the 7-segment displays to also include numbers that are higher than 9 in hexadecimal. Let's look at how we can do this. So right now our design only shows these 10 numbers, but we want to also show A, B, C, D, E, F for the hexadecimal values. Let's look at A. If you look at A, we want the third to be turned off. So let's go to quarters, and turned off means that the value is 1. So I will copy this, and so this is 10, and here I'll set this to 0. So this is 0. This is, let's look at this again. We need 3 to be set to 1. So 0, 1, 2, 3. I will set this to 1. And I will do this for all of the rest of the letters. I will be back when I'm finished. So I have finished adding the rest of the letters. You can see the last number here, that's 15. So this will correspond to F, as you can see in the here. So A, B, C, D, E, F. There will be 10, 11, 12, 13, 14, and 15. And before we compile it and try it, let's implement also the second part. And in the second part, we add one input called add sub. And this will change. If it's equal to 1, it will subtract. And if it's equal to 0, it will add them. So that's what we do now. Right now we have it set to 0, but we also want the possibility to be set to 1. So let's look at quarters, and in our accumulator, I will add one more option here, one more input. This input will be called add sub, and here I will change this. If add sub equals to 1, we want to subtract, else, and if. So if we want to subtract, I will change this to negative value. So if this is, for example, 3, it will be changed to negative 3 and it will subtract. And otherwise, I will just add the value from the input. So this should work. And we can, I'll take these boards and I'll change them here. And also I will change it here. Switch, let's say switch 9 will be for subtraction. So let's try to compile now. Compilation is done, and let's look at the timing analyzer this time. And you can see we have passed the timing constraints. It's still red because of some unconstrained paths, but we care about the timing constraints and we have passed them. If you look at here, the frequency changed from 420 to 370. And here you can see the slack value is positive, and that means the data arrived earlier than they were required. If it would be negative, it would mean they arrived later, and that would mean that we failed the timing constraints. So this works, and let's program the board now. I will let's program the board. And let's look at it. So you can see zeros there, and I will change this to 1, the input to 1, by changing the switch. And if I press the clock, first 0 plus 0 is added, and then we add our 1, 2, 3, all the way to 9, and then you can see A. It's hard to see, but you can see A, then B, C, D, E, and F, and then 1, 0. So it's counting in hexadecimal. I can change the value to some bigger number. And now if I edit, we edit big number, and then we edit again, and now you can see the LEDR here turned on, and that means we have carry. That means we have gone over the limitation of the 8 bits. And we can also try subtraction. If I turn this on, now we will subtract. So I will just change this to 1, so we can see it's subtracting. So you can see value, now it's AF, and you can see it's decreasing. So let's look at overflow. If I put really big negative number, the maximum. So now we have positive number, and we will subtract. Now we will subtract very big positive number like this. Now you can see another, the 8 one turned on, and that means we have overflow. We added two really big negative numbers, and the result was positive. Yeah. So you can see it works. So that's all for today. We have implemented the accumulator circuit. We have implemented this circuit, and next time we will look at multiplication, how to do multipliers in FPGA or digital logic. And if you are interested in convolutional neural networks, you need to also learn about multipliers, because that's another part here. So today we learned about accumulators, and next time you look at multipliers, and that means you are basically good to go to implement a convolutional layer in your own designs. So I hope you found it interesting, and I'll see you in the next one. Bye.